Welcome, my name is Rahul Tiwari, and today I'm going to be talking about my methods and how I carried out the solution to my problem to create a smart backpack. So let's get started. The first slide here is the aggregations of signals slide, and it basically is a representation of the logic that the Decision Subsystem, the DSS, follows to notify the user, the student, that their backpack is incompletely, completely, or optimally packed. Now, as you can see here, the Decision Subsystem recognizes a triggering event. Now, this triggering event is seen through the Decision Subsystem from the backpack module. The backpack module basically houses a sensor that has the ability to determine that the backpack's contents, i.e. books or writing instruments, calculators, can have changed. That means that the backpack is being shuffled through and the user, the student, is planning on moving. Now over here you can see that the backpack also has the ability to find its location, and that location gets pushed to the Decision Subsystem, and the Decision Subsystem can determine, based on currently hard-coded data points that represent the home and school location in the form of latitude and longitude, it can cross-reference it with that data and then determine whether the student is at home or at school, and determine whether the student is going home from school or school from home based on the time of day, which is the third beginning logic point. Now, as you can see here, the triggering event, which is the changing of the contents of the bag that represents that the student is moving, can be paired with either the backpack's location or the time of day. And it helps a Decision Subsystem determine that the backpack is being unpacked or packed at a certain location, and is being unpacked or packed at a certain time. Then we combine all three data points and we come up with a specific solution, which means that the student is packing or unpacking their backpack to leave from home or school. So our student will be sitting at school and finds out that it's time to leave, and will begin shuffling through their backpack and packing their history book and their math book into their backpack. But they'll also pack their English book into their backpack, and then they'll begin leaving. The Decision Subsystem will recognize that the student is leaving because it is a certain time, 4 o'clock, and the backpack has been shuffled through and the student is at school. Therefore, it'll know, because the backpack's contents have changed, that the English book is inside of the backpack, and it'll determine that the student is leaving for home with an English book, a history book, and a math book inside of their backpack. Now on the next slide, we can see that you can combine data such as the daily schedule that the student has, as well as the classes today and tomorrow. Now, the student schedule will allow us to determine that the classes today and tomorrow represent the correct books that should be packed on the backpack. So because the student is packing their backpack, going from school to home at around 4 o'clock, the DSS combines that data with the data provided in the daily schedule, and then it determines that the student has an extra book because the student needs the history and math book for homework. Now, the English book, which is extraneous, will force the Decision Subsystem to notify the user of the specific backpack state, in this case being overpacked. Now, in order for the Decision Subsystem to carry out these logic flows, the backpack has to provide the Decision Subsystem with a certain amount of data. This data comes from these hardware modules, as you can see here. The hardware modules include an Arduino Uno, a GPSB, an XB, and a RFID card reader. The Arduino microcontroller has the ability to control each of these three units, the RFID, the GPS, and the XB, to perform certain functions and push sensor data to the DSS. The RFID card reader allows the backpack to determine the contents of the backpack at any given point in time, and it also is used for determining when the backpack is being shuffled through. The XB is used for pushing data to the decision subsystem using personal area network technology. Now, the GPSB is used to determine the location of the backpack, whether it's at home or at school, using the latitude and longitude locations of the backpack, which is then pushed to the microcontroller, which is then pushed to the XB. Similarly, the RFID pushes the name of the book, which is assigned to a specific coded RFID tag that is tagged on the book. It uses that number code and references it on the microcontroller to a certain book, which then pushes it to the XB and thus to the decision subsystem. The decision subsystem is housed on a Raspberry Pi. The Raspberry Pi was chosen for the decision subsystem because it met the computing power requirements in order to perform a task such as performing the logic flows of the aggregation of inputs from the backpack. In order for me to monitor my Raspberry Pi, I placed a car rear view monitor to act as a terminal display for my Raspberry Pi. Now over here you can see a very, very high level view of the entire system at play. The decision subsystem utilizes Internet of Things technology, which basically allows it to aggregate inputs from multiple locations given a certain amount of computing power. So when the decision subsystem can receive inputs from home, backpack, or school, which basically are three separate points where there are multiple inputs coming in from the sensor networks. The sensor networks can be anything from the temperature of your home to the humidity of your home to the amount of cups that are in your cupboard. The backpack is another data point, which includes data such as the location, the number of books in your backpack, and the ability to transmit using PAN. Now the PAN is represented by these blue lightning bolts here. The backpack communicates with the local decision subsystems inside of the home and the school, and it'll basically push its data to the home and the school, and the home will do any processing it can on its local decision subsystem, and otherwise it'll push data through the internet, through the cloud, to the decision subsystem, which is centralized. The centralized decision subsystem can push notification signals to the user interface, which can be anything from a cell phone to their computer. Now, a slightly zoomed in view on the backpack module shows the GPSB, the RFID tag, and the XB all connected to an Arduino. An Arduino basically processes the data from the RFID and the GPS, as I stated before, and then pushes it to the XB module. The backpack decision subsystem on the school and communicates it with PAN as well. The home communication system is off to the side, as you can see here, and on the next slide you can see the home decision subsystem. The home decision subsystem contains a backpack module, and similarly to the decision subsystem and the school decision subsystem, it contains a PAN module, the XB, and the Raspberry Pi. Once again, the decisions that cannot be made by the home decision subsystem are pushed to the decision subsystem that's centralized, and then it performs decision making to the user interface. As you can see, the school communication system is off to the side as well. Now over here is what I demonstrate in my first revision of the project. In order for me to simplify the decision-making system, the decision-making subsystems, I brought the decision subsystem into single centralized decision subsystem, which takes inputs from a locker module as well as a backpack module, and it pushes that data to my user interface, which happens to be my iPhone, in the form of a text message. It will use SendMail SSL, which will allow me to push data through the gateway of my ISP and receive text through email. My backpack module has not changed, and neither has my locker module. My locker module will act as an auxiliary to provide extra data that allows the decision subsystem to make better decisions, including whether a book has been lost or whether a book is not inside of the backpack or the locker, so it can be elsewhere. Software logic is basically starts off with the triggering event, the book moved event, and it follows the decision-making software as the decision-making logic as I'd presented before. It begins by updating the backpack array with a book, and the backpack array will basically tell me whether I have a certain book inside of my backpack. Now, the GPS module will basically tell me whether I'm at home or I'm at school. Now, our student was at school the last time we checked, and our student wants to go home. And so, it'll basically go check the clock and determine whether it's time to go to school or time to go to home. And given that, it'll check if the backpack is completely packed and dispatch the correct message. Basically, we can have a student who can be at school and is shuffling around their backpack, but in reality is not necessarily at the time to leave school. We do not want our decision subsystem to trigger an event and tell the student that tell the student by short-circuiting and evaluating a short-circuit evaluation that the student is missing a book, because in reality all the student is doing is shuffling their book inside of the school day. It may be the changing of a period, the student may be moving around in the classroom. To prevent this from happening, we have to increase the number of inputs that the decision subsystem gets in order to make a better decision. Now, the at-school portion, the at-school decision will be made, and our student will be going home. And because our student is going home, we have to check if it's packed. And as we know from before, our student packed an extra English book inside of our backpack, so it'll dispatch a message that'll say that the student is overpacked. Now over here, you can see my schematic diagram for my electronics on my locker and backpack module. It's a fairly simple schematic. I wired the GPSB and the XB as well as the RFID and to the microcontroller. The RFID tag uses a serial peripheral interface to communicate with the microcontroller. The XB uses PAN, the 802.15.4 IEEE protocol, which is on 2.4 GHz, to communicate through PAN with the decision subsystem, and as you can see here, it uses a UART interface to communicate with my microcontroller. Now, my Arduino is controlled using an ATmega238 microcontroller. It's an Arduino Uno, and it's connected using another UART interface to my Seed Studio GPSB. Now, as I said before, this component is not in the locker module because I used a fixed component, a fixed GPS location. My GPSB has multiple different interfaces I can use. However, I chose to use the UART interface for simplicity. Now, in order to test my decision subsystem, I have to use a test case scenario table. I need to test the temporal inputs, the incomplete book input, the overpacked backpack input, and the negative temporal input. Which means that I need to check if I shuffle around my books on a Saturday, that there should be no message sent. I need to check that if my backpack is overpacked, that there's no message sent, that there's a message that's sent overpacked. I need to check that if there's an incomplete book, such as only a single book, I need to make sure my backpack is complete. I need to send a correct message. And I need to check my temporal inputs, which tell me on certain days whether my backpack is complete or not. Now over here, these are test cases used for testing the hardware itself. Now in order to test my UART interface, or my SPI interface, I need to connect my RFID reader directly to my Arduino and test whether the history book and physics book have been added to the book list when I swipe their RFID cards across the patch antenna on the RFID reader. Now, this GPS unit, the GPSB, needs to be tested when I move my GPS unit away from home or away from school. Now over here, I need to test my XB communication and determine whether the decision subsystem actually logs the movement of the book, as well as the movement, or logs the movement of a book